Hello friends, so today we are going to solve questions, and these questions are from the chapter electrostatics from the year 1978, 1979, 1980 and 1981. From the year 1978 we have one question, and from the 79 also one, and from 80 we also have one questions, but from 1981 we are having two questions. So in totality we are going to solve 5 questions. So first question, it was asked in the year 1978, and it states that a rigid insulated wire frame in the form of a right angle triangle ABC is set in a vertical plane as shown in the figure. Two beads of equal masses m each and carrying a charges q1 and q2 are connected by a cord of length L and can slide without friction on the wires. So based on this description, we have two questions A and B. First states that considering the case when the beads are stationary, determine the angle alpha, the tension in the cord, the normal reaction on the beads. Part B, if the cord is now cut, what are the values of the charges for which the beads continue to remain stationary? Basic figure is also given to us. We have triangle A, B, C, and the beads are represented in the form of P and Q, and each are having mass m, and charges are given q1 and q2, and this is right angle. Right angle is at A, angle B is given as 30, angle C is given as 60, and PQ is making an alpha angle with our side AB, that is also given to us. Okay. In this case, we first of all we have to find out what will be the alpha angle, and in this case the important part is that the beads are stationary as well as in equilibrium. So we can say that beads are stationary or we can say equilibrium, because they will be stationary only when the beads are in equilibrium. And so let us find out what are the various forces that will be acting on bead P as well as bead Q. And the only difference between the two, between bead P and bead Q, will be the angle. Rest of the forces will be same. So you can say forces on bead P on bead P, and on other side we can write the forces on bead Q on bead Q. The first force is a weight mg, that will be acting vertical downward. Weight mg, and that will be our vertically downward, and that will be same for q also, because the mass is same for both p as well as q. So that will be weight mg, and that will be vertically downward. Next is tension in the string. Tension, let us suppose, given as T, that acts along the string. Tension along the string, and same for our Q also. Tension T along the string. And there will be also the force F, that is of electrostatic force, or we can say electric force. Then we have our electrostatic force, and that will be also, you can say, electrostatic force denoted as F, that will be also along the string. And same here. Electrostatic force F along the string. And finally, we are going to have the normal reaction. Okay, and normal reaction will be different for both. You can say normal reaction for P, let us call that as a N1, and it will be perpendicular to the wire. Perpendicular to the wire. And here also we are going to have normal reaction N2 perpendicular to wire. Okay. And let us consider first of all for bead P, and we can just draw an approximate figure for that. So we have, suppose this is our bead P, and the normal will be our perpendicular to the wire. Let us draw the perpendicular to wire, and this is normal our N1. We have our mg, that will be acting vertically downward. Okay. And we have a angle alpha that is making string. Okay, so let us suppose we have our string something like this. Now this angle is given to us as alpha, and we have this angle is our 30 degree. So obviously this angle will be over 60, and we can divide mg into two components. One will be our mg cos of 60, so this part will be our mg cos of 60, and to the other side we are going to have mg sine of 60. Sine of 60. And the string, this is our P. So along the string there will be two forces. One will be tension and other one will be the electrostatic force. So the net force will be about T minus F. And this T minus F we can divide into further two components. One will be our T minus F cos of alpha. So this comes as T minus F cos of alpha. And along this line it will be coming as T minus F sine of alpha. So these are the forces that is acting on bead. You can say P. Similarly, we can draw the forces that will be acting on bead Q also. Okay. And we have this is a bead Q. First of all, we can just draw the normal, that we have N2 and we have our mg, and this angle is given to a 60 degree. Okay. And we can just complete the string. So this is our point P, and this is our point A. This is our 90 degree. So this angle is given to us alpha. So we get this angle will be our 90 minus of alpha. Okay. So therefore, and similarly along the string, so this is a connected string, and we can say this force will be T minus F. Okay. And we can divide this into two components. One will be along this line, that is our T minus F, and it will be cos of 90 minus alpha, 90 minus alpha, and the other component will be along this direction, that will be our T minus F, and this is our sine of 90 minus alpha, 90 minus alpha. Okay. And this angle is nothing but our 30 degree, because if we join it downward, this will be making a 90 degree here, and similarly it is true for here also. This is about 90 degree. Downward we have our mg, and this mg once again we can divide into two components. Will be along this line, which will be coming as mg cos of 30, and other one will be along this line coming as mg sine of 30, sine of 30, and this is our q. And this angle will be nothing but our alpha. That is not required, anyways we can say it, write it, not a big problem. So this T minus alpha, T minus sine of 90 minus alpha, we can write this as T minus F cos of alpha, and on the other side we can write this as T minus F sine of alpha. And these are the all respective forces acting on the P as well as Q. Now it is given that everything is equal, bead P and Q are equilibrium. So let us discuss for bead P. So we say equilibrium of bead P. Equilibrium of bead P. Therefore, the forces which are along the wire will be our mg cos of 60, and that is T minus F cos of alpha. So their summation will be equal to 0, or we can say from here that mg cos of 60 will be equal to, we have this as T minus F, and this will be our cos of alpha. And perpendicular to this we get our N1 will be equal to, we have a mg sin 60 mg sin 60 and plus T minus F, and we have sine of alpha. And similarly we can write for bead Q. Equilibrium of bead Q, we get first force will be equal to our T minus F sine of alpha is equal to mg cos of 30. We can say our mg cos of 30 is equal to T minus F sine of alpha, and other force we get is our normal, that is our N2, which will be equal to mg sine of 30 plus T minus F cos of alpha. Mg sine of 30 plus T minus F cos of alpha. And we can, first of all, we need to find out our alpha. Then we can just sort it out, and we can write, let me name them equation number 1, 2, 3 and 4. So if we divide equation 1 and 3, sorry, and you can say dividing equation 1 and 3, we get mg cos of 60 and divided by mg cos of 30. Mg cos of 60 divided by mg cos of 30, and that will be equal to T minus F cos of alpha and we get this as T minus F sine of alpha. Here mg T minus F cancels out, and we can just, you can say, reverse the equations, and we can write this sine alpha upon cos alpha upon cos alpha, and we can write this as cos 30 divided by cos 60. Cos 30 divided by cos of 60, and sin alpha upon cos alpha is tangent of alpha, so we can write this as tangent of alpha, and on the other side we can write this as sine of 90 minus 30, that is sine 60 divided by cos 60. So we can write this as sine 60 divided by cos 60, which will be also giving us tangent of 60, which gives us that our alpha is equal to over 60 degree. So we got our alpha. Next we need to find out the tension of the cord, and tension of the cord we just found out of alpha. We can use any of the equation and find out our tension. So let us suppose we use equation. You can say that for bead Q, we can write we have our mg cos of 30, mg cos of 30 is equal to t minus f, and we have this as sine of alpha. Sine of alpha, we substitute, we get this as mg, and we can write this as cos of 30 can be written as sine of 60 will be equal to t minus f, and here also we have sine of 60. Sine of 60, sine of 60 cancels out. This gives us that our mg is equal to T minus F, and F is the electrostatic force, of which the formula we already know. So we can say our tension T will be equal to over mg plus F, which can be written as mg 1 plus, and that force F is our electrostatic, that is 1 upon 4 pi epsilon naught product of the charges divided by the distance between the two, which is given as L and its square. So this is our tension in the string, that is our T. So this is tension T in the string. And next it says that we have to find out the normal reaction of the beads. Okay. And for that we can use the equation number 2 as well as 4, because normal reaction will be different. And T minus F is mg, which are also we are going to use in this particular solution. So we can say for bead Q, sorry, let us start with P, and we have our N1 is equal to mg sine 60 T minus F sine alpha. Mg sine 60 plus T minus F, and this we have sine of alpha. We have our alpha is 60 and T minus F is equal to mg. So we can also use this particular equation. Therefore, we can say that our N1 is equal to our mg, and we have sine of 60 plus mg, and this we have our alpha is our 60 sine of 60. So this gives us that our N1 sine 60 is root 3 by 2. So we get twice root 3 by 2 multiplied by mg. This comes as twice root 3 by 2 multiplied by mg, 2 and 2 goes away, so we are left with our N1 is equal to root 3 times mg. And similarly we are going to solve for bead Q also. So you can say for bead Q we have our N2, and that N2 is mg sine 30 and alpha is cos 60. We have mg sine 30 plus t minus f, and we have cos of alpha. T minus f is our mg, so if substitute it, we can write that our N2 is equal to mg sine 30 plus mg cos 60, and cos 60 we can write it as sine 30. So we get this as mg sine of 30 plus mg sine of 30, and sine 30 is 1 by 2, so we get our N2 is equal to twice into 1 by 2 times mg. Here 2 goes with 2, and this gives us that N2 is equal to our mg. So this completes all our part A. In part B, it states that the cord is cut. But even though the cord is cut, it states that the charges are still in equilibrium. And when cord is cut, only force that is going to vanish or comes to zero will be tensional cord, that is T. So you can say that cord is cut, so which basically means our tension T is equal to 0. But the beads remain stationary or in equilibrium. The electrostatic force is going to balance the components of the gravity, that is our mg. So we can just put T is equal to 0 in equation 2 and 3. Sorry, not equation 2 and 3, but in equation 1st and 3rd. Okay, because we are not interested in normal reaction, we are only interested in finding out the value of charges. The value of charges we can use equation, or we can also use equation 2 and 3, but there we have to substitute the value of N1 as well as N2. So much better option is using equation 1 and equation 3. So we can say for bead P, we can write that we have it as F cos of alpha is equal to mg cos of 60. F cos of alpha is equal to mg cos 60. We substitute alpha, that is our 60 degree, so we get F of cos 60 is equal to mg cos 60. And for bead Q, we can say that we have it as F sine of alpha and mg cos of 30. So we have F cos of alpha is equal to mg sine of 30, and if we substitute it, we get mg cos of 60 is equal, sorry, F cos of 60 is equal to mg sine of 30. and from both the equations, because these two will cancel out and these two will also going to cancel out, because cos of 60 we can write it as sine of 30, so these two also cancel out. Therefore we get that our force F is equal to our mg. And there will be negative sign, but that is only we are only interested in magnitude, because if we put tension equals 0, so there is also negative sign in equation 1 as well as negative sign in equation 3. Okay. But considering only magnitude, we get F is equal to mg, and from here we get 1 upon 4 pi epsilon naught q1 q2, and this comes as length square, L square is equal to mg. So this gives us that our q1 q2 will be equal to 4 pi epsilon naught mg times L square. I think this was, yeah. Okay. And next question. We are given, it was asked in the year 1979, and it states that a pendulum bob of mass 80 milligram carrying charges 2 into 10 to the power minus 8 coulomb is at rest in horizontal uniform electric field of 20,000 volt per meter. Find the tension in the thread of the pendulum and the angle it makes with the vertical. So in this case, we have a pendulum. We can just draw its approximate figure. Suppose this is the mean position of the pendulum, and because of the electric force which will be acting in this direction, that is our Fe, the pendulum, let us suppose, makes an angle of theta with the vertical, and it comes to an equilibrium position here. And then the force C which will be acting here will be over mg in the downward direction, and there will be tension T, and we have a force due to electric field, that is of Fe, which will be equal to charge multiplied by electric field. And we can divide this tension into two components. This angle will be our theta, so we get this as T cos of theta, and we get T sine of theta. So therefore, for equilibrium, of bob, the forces will be balanced in vertical as well as horizontal independently. Therefore we can write that T cos of alpha is theta is equal to mg, and we get our T sine of theta is equal to our Fe, which is nothing but our Q times E. Let us call this equation 1 as well as equation 2. And if you can say if we square them and add respectively, squaring and adding 1 and 2, on the left side we are going to get this as t square, which can act as common, and then will be our cos of theta plus cos square theta and sin square theta is equal to, and on the right side we are going to get mg whole square plus q times E whole square, and this term will be equal to our 1. So we get our T will be equal to our mg whole square plus QE whole square and its square root. And if we divide equation 2 by 1, or we can substitute the values rather, let us sort it out. And if we substitute the value, mass is given to us as 80 milligram, 80 milligram. So this we get as 80 into 10 raised to power minus 6 into our G, that is our 9.8 whole square plus 2 into 10 raised to power minus 8, and electric field is given as 20,000 whole square and its square root. So we get our tension T will be approximately equal to 8.79 into 10 raised to power minus 4 newtons. We need to find out theta also. So you can say, dividing equation second by first, we get this as sine of theta divided by cos of theta is equal to QE divided by mg, or we can say tension also, which will be cancel each other. So we get our tangent of theta is equal to QE divided by our mg, and this gives us our theta. Now we substitute the value. Charge is our 2 into 10 to the power minus 8, electric field is our 20,000, mass is our 80 milligram, and 9.8, and our theta will be a tangent inverse of this value. Tangent inverse of 2 into 10 to the power minus 8 into 20,000, 80 into 10 to the power minus 6, and 9.8, and we get approximately equal to 27 degree. So we found out both tension and angle it makes with the vertical. Next question. It was asked in the year 1980, and it states that find the potential difference between points A and B and between points B and C in the steady state condition. We are given the figure, and this figure we have two resistors. Let us call this as R1 as well as our R2, and rest of things are all capacitors. So let us call this as our C1, this our C2, and we have this our C3, C4, and we have C5. And we have to remember that we have to find out the potential at steady state. And at steady state, the behavior of the capacitor is entirely different. They are all going to act as open circuit. You can say that at steady state, we have our capacitor will be acting as open circuit. So from the, if we see this figure carefully, we can understand that the mainly this entire block only constitutes of the capacitors. So it means this entirely be acting as open circuit. So we can just approximately draw the figure, which will be something like this. and the points given as A, this is C, and this point is D, and this point is E. We have our R1 and we have our R2. It is given as voltage as 100 volt. So as the entire circuit is open circuit, the current through the circuit will be equal to 0. So from here we can say that current through the circuit will be equal to 0. So which basically means no current will be flowing through R1 and no current will be flowing through R2. Okay. So we can say from here that current through R1 0 and current through R2 is also equal to 0. Or indirectly we can say that the both ends of R1 as well as R2 will be at same potential. Okay. So it means that potential at A will be same that of the potential on its right side, and similarly the potential at, you can say, at C will be same, that is will be a potential at E. We will write the values later on. So let us solve the capacitors combination. Even though the current is flowing through the capacitor is equal to 0, but the voltage is going to exist, which will result in the potential difference. And let us solve these capacitors. So first capacitor we need to solve is our C1 and C2. These are in parallel. So we can say that capacitor C1 and C2 are in parallel. Therefore we can say our this C net 1 will be equal to C1 plus C2, which comes as 3 plus 3, giving us 6 microfarad. Similarly, on the other side we have our C4 as C3. These two are also in parallel and of same value. So we can say capacitor C3 and C4 are in parallel. So we can say C net 2 will be equal to C3 plus C4, which gives us 1 plus 1 is equal to 2 microfarad. So based on this we can just resolve the circuit and draw an equivalent one, and that equivalent circuit will be something like this. This is our C net 1, whose value is given as 6. This is point B, and we have our C net 2, whose value is our 2 microfarad, and in the parallel opposite end we have its 1 microfarad, and we have our resistance, that is our R1, and then we have resistance, that is our R2. So this is our R1 and this is our R2, this is our A and this is our C. Rest of the things we need not write out, because we are only interested in a potential difference between A and B and C and B. And like I said, that we are going to have capacitor, the current through this R1 and R2 is equal to 0. So because of this is our 100 volt given to us. So this entire voltage will be in parallel with our 1 microfarad, and that we denoted as C5. So this was our C5. So you can say that the potential difference, potential drop, let me not difference, drop, then we are going to come to the difference. So you can say potential drop across R1 and R2 is 0. Therefore, we can say that the potential difference across 1 microfarad, that is C5, potential difference across C5 will be equal to 100 volts. Okay, so it means this 100 volt will be across here. Let me draw this part on the lower side. So we get the potential difference is across this 100 volt. Okay. And we can clearly understand that this setup of, we have this as 6 microfarad as well as 2 microfarad. These are in series. So this 100 volt will be also the parallel across both the series capacitors. So we can also say that potential difference across, you can say, series C net 1 and C net 2 will be also equal to 100 volt, and depending upon their respective capacitance individual values, they will be in ratio. Okay. So the capacitance are our 6 microfarad and 2 microfarad. So the corresponding ratio is 2:6, or we can say 1:3. So we can say that the potential difference, which is about 100 volt, is divided between C net 1 is our 6 microfarad, C net 2 is our 2 microfarad, is divided between 6 microfarad and 2 microfarad as inverse ratio of their capacitance, as inverse ratio of their capacitance. That is, in the ratio, that is inverse ratio. So ideally it should be 6:2, but inverse will be 2:6, or from here we can say 1:3. So we can write that VAB will be equal to potential difference across 6 microfarad, ratio will be inverse, that will be coming as 1/4, multiply by 100 volt, which is coming as 25 volt, and next is our VBC, which is potential difference across 2 microfarad, which will be coming as reverse as 3 by 4, multiply by 100, and that comes of 75 volts. So we got the potential difference across B, C as well as across A and B. Next question. It was asked in the year 1981, and it states that a charge Q is distributed over two concentric hollow spheres of radius r and capital R, which is greater than small r, such that surface densities are equal. Find the potential at the common center. So we can just draw an approximate figure for that. We have concentric hollow spheres. So we have an inner sphere whose radius is given as small r, and we have a outer sphere whose radius is given as capital R. And we are given that a charge Q is distributed along this. It means total charge on this internal as well external sphere should be equal to our capital Q. Summation there. And we say that we have a charge of Q1 on small r and our Q2 on capital R. And we are also given that their surface charge densities are equal to each other. So we assume that charge on sphere of radius small r, charge on sphere of radius small r is our Q1, and radius capital R is our Q2. And surface charge density for this small r, let me write it separately. So you can say surface charge density, surface charge density for radius small r, let us suppose is sigma 1, which will be equal to our Q1 and its area A1, and we can write this as Q1 upon 4 pi small r square. And similarly we can say for radius capital R, surface charge density is our sigma 2, which will be equal to our Q2 upon A2, or we can write this as Q2 upon 4 pi capital R square. And we are given that surface charge density is same. It means Q1 is equal to Q2. You can see, but sigma 1 is equal to sigma 2, not Q1 Q2. This is given. So we substitute the respective formulas. We get this as Q1 upon 4 pi small r square is equal to Q2 upon 4 pi capital R square. 4 pi goes away, and this is going to give us the relationship between our Q1 and Q2. So we can say that Q1 upon small r square is equal to Q2 upon capital R square. Later on we can use this relationship as per our convenience. And let me sort it out here only. So we can say from here that our Q2 is equal to capital R square divided by small r square multiplied by Q1. And the total charge is given as capital Q. Total charge given as capital Q, so it will be equal to summation of Q1 plus Q2. We substitute value of Q2, we get this as Q1 plus capital R square divided by small r square multiplied by Q1. And we can take Q1 as common, so we get this as our Q1 will be equal to, we get this as small r square, and this will be r square plus capital R square and multiply by Q. And then we substitute this into the main equation, that is Q is equal to Q1 plus Q2. From here we get our Q2. So we can say our Q2 will be equal to capital Q minus our Q1, and we get this as capital Q minus small r square divided by r square plus r square multiplied by Q. Taking LCM, the small r square is going to cancel out, so we get our Q2 will be equal to capital R square divided by small r square plus capital R square times capital Q. So this we get our charge Q2, and we need to find out the potential at the center. Potential at the center, let us put this is given as O. So you can say the potential at the center O. Potential at center O, and we have two concentric circles, that is our small r and radius capital R. There we can say that potential at center O due to radius small r, let us call that as a V1, which will be equal to 1 upon 4 pi epsilon naught, and charge is given as our Q1, so this will be Q1 upon R. And similarly we can say because of the radius capital R, let us call that as our V2, we are going to get 1 upon 4 pi epsilon naught, and this is our Q2 upon capital R. And the total potential at the you can say center will be the algebraic sum, that is V1 plus V2. Total potential at center, that is our V will be equal to V1 plus V2. So it is a basic algebraic sum, charges are same, so it will be sign will be positive. So we can say our V, we can write that our 1 upon 4 pi epsilon naught we can take as common, and we have this as Q1 upon R plus Q2 upon capital R. And we already know the relationship between Q1 and capital Q and Q2 as well as capital Q. So we substitute them, we get 1 upon 4 pi epsilon naught, and capital Q we can take as common. So inside we are going to get this as 1 upon r, and this comes as r square plus capital R square plus 1 upon r, and we have capital R square divided by r square plus capital R square, and charges q is taken as common here, and we get this r square cancel out. So we get our potential V will be equal to q upon 4 pi epsilon naught, and this will be equal to, denominator is same, we can further take its common, so we get this as our r plus capital R divided by r square plus capital R square. Okay, so this is our potential at the center, common center. Okay, so we found out our, I think that is only thing required. Yeah, so this was the only thing required. Next question, and it was also asked in the year 1981, and it states that an alpha particle of energy 1 mega electron volt is scattered through 180 degree by a fixed uranium nucleus. The distance of closest approach is of the order of. So here we can use the conservation of energy principle, because as the alpha particle will be coming close to our uranium nucleus, and there will be a decrease in its kinetic energy, which will be resulting in increase in the, you can say, will be increase in the potential energy. So we can just write that basic principle. So we can say from conservation of energy, decrease in kinetic energy, decrease in kinetic energy will be equal to our increase in potential energy, and it asks the distance of the closest approach. So let us assume that the minimum distance, the alpha particle, let me draw the figure. So we have a alpha particle as well as our uranium nucleus, and we can assume that the closest they can come is our given as R minimum. So we need to find out this particular distance. Therefore we can say that the kinetic energy of alpha particle is given to us as our 5 mega electron volt. So we can say that our 1 upon 4 pi epsilon naught, and we have this as R minimum, and this will be our ZE square, and divided by our R minimum will be equal to our 5 mega electron volt, and we can just substitute the values, or let's calculate the formula first of all. So we get our R minimum will be equal to, we have this about 5 mega electron volt, and that will be coming as 5 into R minimum will be equal to our Z E square divided by 4 pi epsilon naught and multiply by 5, and this will be 1.6 into 10 raised power, this is 5 mega, so this comes as minus of 30, and 4 pi. Okay, now we can just easily substitute the values. We get this as R minimum will be equal to 1.4 pi epsilon naught is our 9 into 10 raised power 9 into 2, and we get this as 92 times 1.6 into 10 to the power minus 19 whole square, and divided by 5 into 1.6 into 10 to the power minus of 13, and this will be coming approximately equal to 5.3 10 to the power minus 14 meters, and it is in centimeters. So we can say our R minimum approximately in terms of the order will be 10 to the power minus 12 centimeters. We are only asked the order. So this comes as 10 to the power minus 12, that is option number C is the correct one. C is the correct one. So these were the questions with total of, we can say we did 6 questions, and year 1978, 79 and 80 were having each 1 question, and 81 was having 2 questions. So this completes all the questions. Thank you.